Hello, my name is Jan Gerlach and I'm from the Institute of Forming Technology and Lightweight Components.
And my name is Lennart Sobisch and I'm working at the Institute of Mechanics. Together, Jan and me are participating at the Collaborative Research Center where we work on the service project. The service project acts as the interface between the three project areas: process technology, characterization and modeling.
Lennart and I already know each other from our studies, and we are happy to continue our work in the service project during its third funding period. What I particularly like about the Collaborative Research Center is the interdisciplinary environment. I believe that only by combining different expertise, we are able to achieve new results.
And some insights about these results we want to show you in this video.
The majority of my tasks are carried out here in the office, where we forge the link between the three project areas by developing software tools and frameworks which empower the technology projects to conduct predictive simulations of their processes. A good example for this is the prediction of damage evolution in cold forging. We developed a parameter identification tool freely accessible on GitHub and calibrated various damage models. This calibration was not limited on force displacement data, but also encompassed full field data and void measurements received from the characterization projects. With the calibrated models at hand, we were able to predict the void evolution in cold forging. Another topic is the development of time-efficient models. To this end, data-driven damage evolution has been trained solely based on experimental void measurements, and thus, unlike conventional evolution laws, is not restricted to assumptions regarding the respective equation. To determine the influence of the experimentally observed void fraction on the mechanical properties, the data-driven damage evolution will be linked to the elastic and plastic properties within a constitutive framework in the future.
To make the sophisticated material models which have been developed in CRC 188 available for actual process simulations, the implementation of these models into commercial software is a key objective of the service project. To further understand the requirements for such a simulation framework, let us consider the example of a forward extruded part. This process yields a temperature increase typically ranging up to 200 degrees Celsius. As a consequence, the developed simulation tools must be able to capture non-isothermal material behavior. In general, damage and degradation models yield mesh-dependent finite element results. This leads to a physically not consistent prediction of the process. As a consequence, the developed damage models of CRR incorporate non-local damage formulations. To address all of these challenges, an implementation framework for the finite element software used by the technology project has been developed. The application to the benchmark problem of an extrusion process can be seen here. The described simulation approaches yield a very high computational effort ranging up to multiple days. Because of that, we want to further increase the efficiency of our simulations in the third funding period. We will investigate model order reduction strategies and incorporate them into data-driven approaches. Additionally, we want to include explicit solver structures into our software tools to cover a broad range of applications. We really appreciate your interest on the research results of the CRC and are looking forward to present you future results of our investigations.